In the diagram below, a small metal sphere A on an insulating rod has a charge of minus 80 times 10 to the power minus 9 coulombs. And then 7.1 says, describe the term electric field in words, right? An electric field is a region of space in which an electric charge experiences a force. A region in space in which an electric charge experiences a force. Basically, we're saying that E is equals to F divided by Q, right? That's the formula for electric field. A region in space where an electric charge will experience a force. And then 7.2 says, calculate the number of electrons sphere A has in excess, right? So the number of electrons a sphere will have in excess will be equals to its charge divided by the charge of an electron, assuming it has a negative charge, right? Because if it has a positive charge, then it doesn't have any electrons in excess. In this instance, we're going to have minus 80 multiplied by 10 to the minus 9 divided by the charge of an electron, which is minus 1.6 times 10 to the minus 19. So I'm getting 5 times 10 to the 11 electrons. So this sphere has 5 times 10 to the 11 electrons in excess. And then we are told now that sphere A is now kept vertically above another sphere B of mass 0.01 kg lying on a horizontal insulated surface. The charge on sphere B is plus 120 times 10 to the minus 9. Sphere A is closely brought closer to sphere B in order to pick it up. Ignore the effects of friction. Okay, and then 7.3 says that draw a diagram that shows the electric field pattern between spheres A and B. So sphere A is negative, let's put it here, and then down here let's have sphere B, which is positive. So the electric field on sphere B, which is positive, will be pointing out, while the electric field on sphere A, which is negative, will be pointing towards itself, right? So let's have something like that. So for sphere A, the electric fields are pointing towards it, and then for sphere B, the electric fields are pointing out, right? And sphere A and B will attract each other. So let's demonstrate that using our electric field lines, right? Yeah, so at the end of the day, you're going to get something like this. If you want to be more precise, sphere B has a greater magnitude compared to sphere A. So you can put more electric field lines pointing out of sphere B, since it has a greater magnitude. And then 7.4 says, at a certain height h, sphere B is just lifted off the surface due to its attraction to sphere A. Just lifted off, right? Let's note that, just lifted off. And then draw a free body diagram showing all the forces acting on sphere B at this instance. So let's talk about the keyword just in this statement line. So if it is just lifted off, then that tells us that the force that is lifting it off and the force that are keeping it down, they are very, 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 very close to each other. They are approximately equal. So that's why it is just lifted off for a split of a second, right? So let's look at sphere B and do some analysis. So if sphere B is being lifted off, it's going to be lifted off by the attraction from sphere A, right? So let's have an arrow pointing up here and demonstrate that this is FA on B, and then what's keeping it down is gravity, right? Because it is said to have a mass of 0.01 kg. So let's have Fg here. So we need these two lines to be approximately equal to each other because the sphere was just lifted off. And then 7.5 says calculate the height h in the diagram at this instance, right? So we definitely gonna use the free body diagram of sphere B, right? Because that's the only information we have. So we're gonna say that FA on B is equals to FG. So FA on B will be K Q1 Q2 divided by R squared, and Fg will be the mass multiplied by the gravity. So what is the value of K? We know fully well that K is 9 times 10 to the 9. The charge on Q1, let's say Q1 is A, that will be 80 multiplied by 10 to the minus 9. Don't forget, we're only interested on the magnitude of the charges and not the direction. And then for B, we're going to have 120 times 10 to the minus 9, and then we divide everything by R squared. So R in this instance is H, right? So we're going to have H squared, which is equals to the mass 0.01. Gravity is 9,8. Right? So now we're basically solving for H squared. So if we cross multiply, H squared is going to be multiplied with 0.01 multiplied by 9,8, right? And then we're going to end up dividing both sides by 0.01 multiplied by 9,8. So we're going to have H squared being equals to 9 times 10 to the 9 multiplied by 80 times 10 to the minus 9 multiplied by 120 times 10 to the minus 9. And then this we are going to divide it by 0.01 multiplied by 9,8. So now we can take square roots on both sides, right? So we'll say H squared to the power 1 divided by 2 is equals to this entire expression to the power 1 divided by 2. So H will be equals to 0.0297 meters, right? And then let's move to 7.6. And now we are told that sphere A is now placed on the horizontal insulated surface a distance x from sphere B as shown in the diagram below. P is a point between A and B, which is 0.05 meters from B. The magnitude of the net electric field intensity at point P as a result of the presence of sphere A and B is 54.45 times 10 to the 4 nano per Coulomb. And then 7.6 say draw a labeled vector diagram indicating the directions of the electric field at point P as a result of spheres A and B. So point P is the point charge, right? So we always assume that it's positive. And then sphere B is positive, right? And then sphere A is negative. So how do point P and sphere B interact? They repel each other, right? That means that the vector of charge B on P will point in that direction. And then how does sphere A and sphere P and point charge P interact? They attract each other. So A on P will be in that direction also. This will be electric field due to B, and this will be the electric field due to A. And let's move to 7.7. 7.7 says calculate the distance x between spheres A and B. So we are given the net electric field and the magnitude of the charges, right? And the distance between the point charge and one charge. So it should be obvious to see that we're going to use E net is equals to EB plus EA, right? So E net is 54.45 times 10 to the power of 4. And then the electric field due to B will be K. I won't substitute anything for K for the sake of space, right? And then the magnitude of B is 120 times 10 to the minus 9 divided by R squared, the distance between P and B, which is 0.05 squared. And then plus K again for the sake of space, the magnitude of A, 80 multiplied by 10 to the minus 9 divided by R squared. So R squared here will be the distance between A and P, right? Let's just put Y there. So let's put Y squared, right? So we're looking for X. You can see that X will be Y plus 0.05, right? So after we found Y, we basically have X. So if we do that, we can take this expression here to the left hand side, right? So we're gonna have 54,45 multiplied by 10 to the power 4 minus 9 times 10 to the power 9. I'm substituting K now, multiplied by 120 times 10 to the minus 9 divided by 0.05 squared. And then this will be equals to 9 times 10 to the power of 9 multiplied by 80 times 10 to the minus 9 divided by Y squared, right? So now I can rearrange this equation in attempt to find Y squared. So basically, if you have A is equals to B divided by Y and you want to find Y, you're going to cross multiply, get AY is equals to B, so Y will be B divided by C. You can see that B on our equation is this expression here, and then A on our equation is this entire expression, right? So let's rearrange it so that we can find Y ultimately. So we're gonna have Y squared is equals to 9 times 10 to the power of 9 multiplied by 80 times 10 to the minus 9 divided by this entire expression. So that's essentially what we're doing there. And then after this, we will take square roots on both sides. So we have Y squared to the power half, and then this entire expression to the power half. And then if you do that, you're gonna get Y is equals to 0.08 meters, right? So X will be 0.08 plus 0.05, which is 0.13 meters.
7.1 says that state Coulomb's law in words, that is that the magnitude of the electrostatic force that one point charge exerts on another point charge is directly proportional to the product of their charges and inversely proportional to the distance between them. That is basically the formula for electrostatic. You can see that F is directly proportional to the magnitude of the charges and inversely proportional to the square distances between the point charges. So let's move ahead. 7.2 says calculate the distance R between the spheres. If you look at the diagram on the left hand side, we have sphere R and sphere S, and then we're supposed to calculate the distance R in between. Yeah, if you go through the equation, I didn't go through it in the video just to save you some time. There it says sphere R. Look at the left hand side there. I'm just going to highlight it. Yeah, there we have it. It says sphere R exerts an electrostatic force of magnitude 1.2 times 10 to the negative 3 newtons on sphere S, right? So if we're using this formula, F equals to K Q1 Q2 divided by R squared, we know that F will be 1.2 times 10 to the power minus 3 equals to, then K is a constant, that is 9 times 10 to the power 9, and then Q1 will be R in this instance. So R, the charge is 5 times 10 to the minus 9 multiplied by the charge of sphere S, which is minus 6. But then on electrostatic force, we are only interested on the magnitude. So in this instance, there's no need to include the sign. So it's just going to be 6 times 10 to the minus 9 divided by r squared. R squared is what you are interested in. So from here, it's quite simple. The only variable we have is r squared. So you just do a bit of math and you solve it. So let me go ahead and do that. I'm going to cross multiply. I'm going to multiply the left hand side by r and then multiply by the right hand side by r. So that will give me r squared equals to 9 times 10 to the 9 multiplied by 5. Okay, some technical issues. 5 times 10 to the minus 9 multiplied by 6 times 10 to the minus 9 divided by 1.2 times 10 to the minus 3. So now what's left is taking the square root on both sides. So I'm going to get r equals to 9 times 10 to the 9 multiplied by 5 times 10 to the minus 9 multiplied by 6 times 10 to the minus 9. Everything divided by 1.2 times 10 to the minus 3. And then to the power 1 over 2. That's taking the square root. Equals to, let me put that in the calculator real quick and see what I get. So we have 9 times 10 to the 9 multiplied by 5 times 10 to the minus 9 multiplied by 6 times 10 to the minus 9 divided by 1.2 times 10 to the minus 3, everything to the power 1 divided by 2. That gives me 0.015 meters. So yeah, that's the value for r. Let's move ahead. 7.3 says draw a free body diagram for sphere S. Okay, let me go ahead and do that. But then, like all the time, if you draw a free body diagram for an object, you are probably going to use that free body diagram on the question that's going to follow. Okay, so let me go ahead and just draw the free body diagram. So this sphere S, I just highlighted in green on the left hand side. So on sphere S, there is a pulling force from sphere R, right? So it's being pulled by sphere R because R is of an opposite magnitude to sphere S, so it's going to pull it, and then it's connected to point P by a string. So going up, we have some tension there, and then obviously we have gravity, and then it's on a surface. So because it's on a surface, we're going to have the normal force. And then what else do we have? We have the tension, we have the weight, we have the normal force, we have the F, the force applied by R. So I think, yeah, that's it, we're done. And then let's move ahead. 7.4.1, the question says calculate the tension in the string. So as soon as I think about tension, the first thing I run to is F net equals to MA. This is because almost all the time when the question asks me to calculate tension, I use this formula. So I'm starting here and then I can move elsewhere. And then if you've watched other of my videos, I recommend that you go watch them. You will know exactly what to do there. We're going to, okay, we're supposed to find the tension. The spheres are stationary, right? So we know that F net equals to 0. Okay, so let's just put that there. So there it is, we have 0 because acceleration is 0. So what we're going to do, we're going to write the biggest force and then subtract all the other small forces. But you can wonder like which one is the biggest force because it's stationary. So that means that all the forces are balancing out. We have two forces pulling the sphere down the incline, and then the tension is pulling it up the incline, right? The first force is the force being applied by the sphere R, and then the force of gravity parallel to the plane. So those forces are equal to the tension. So the tension is bigger than those two forces. Okay, so let me go ahead and do that. So I'm going to have tension minus Fg parallel minus F applied by R, right? Which we are given as 1.2 times 10 to the minus 3 Newton. So the tension is our unknown. So there we have it. So this is going to be, let's take Fg parallel and Fr to the other side. Therefore, we're gonna have Fg parallel plus F, the electrostatic force exerted by R, right? So this is T equals to Fg parallel on an incline. We know that that gives us the mass multiplied by gravity, and then sine of the angle, right? Sine theta plus that one we are given is 1.2 times 10 to the minus 3 Newton. So now the mass of sphere S, if you write through the equation, you can see that the mass of sphere S is given as 0.01 kg. Yeah, there it is. I just covered it then. So we have 0.01 kg multiplied by force of gravity 9.8 sine of there we have the angle 25 degrees plus 1.2 times 10 to the minus 3. So let me go ahead and put that in my calculator real quick. Get 0.01 multiplied by 9.8 sine of 25 plus 1.2 to the minus 3. That gives me that is equal to 0.042, so that will just be 0.04 newtons. So that's the tension that is between sphere S and point P. Let's move ahead. Last but not least, 7.4.2 net electric field at point P. We know that the equation for electric field is E equals to K Q divided by R squared, or is equals to F divided by Q. So so in this question we're going to use this formula E equals to KQ divided by R squared instead of this formula here, because we don't have the charge of P, right? So we cannot use that formula. So let's go ahead and do that. But then before we carry on, one thing to realize is that S and R have opposing effects. R is positive, so if P is positive, it will be getting repelled, but then if it's negative, it will be getting pulled. And then sphere S, it will do the opposite. If it is negative, it will attract, and then if it is positive, it will pull apart. So we have to put a negative sign between either the electric field for sphere R or the electric field for sphere S, right? So that will be E net equals to E exerted by Q plus E exerted by S, right? So okay, E net equals to so Q exerted by R, I'm sorry, said Q instead of R. So the K, we know what K is. That's 9 times 10 to the 9, and then Q, and then R, the charge for R, that is 5 times 10 to the minus 9 divided by R squared. Okay, the distance between R and P is, look at the left hand side, the sum of this distance and this distance, right? So it means that here on the denominator we're supposed to have R. We calculated it was 0.015 meters, so that is 0.015 plus 0.03, and then we square that, and then plus 9 times 10 to the 9, and then the charge of sphere S minus 6 times 10 minus 9 divided by the distance is 0.03 squared, which is equals to, let me put that in the calculator real quick and see what I get. Yeah, that is giving me minus 37.78 nano per coulomb. And then yeah, that's it for this question. We're done. So the key points, the things to remember, if you're calculating F using K, Q1, Q2 divided by R squared, no need to include the sign of the charges. But then if you're calculating the electric field exerted by 2-point charges on another point, then that's where you have to use, you have to consider the sign, right?
We have a sphere A here of charge minus 5 microcoulombs hanging from a ceiling, right? By means of a light inextensible string. And then 100 millimeters away, we have a point charge P. And then the first question, 7.1.1 says, did charge the sphere A lose or gain electrons to acquire a charge of minus 5 microcoulombs, right? So if a sphere was neutral, right, and then now it has a charge of minus 5 microcoulombs, did it gain or did it lose electrons? We know fully well that electrons are negatively charged, right? So if it becomes more negatively charged, then it gained electrons, right? So for 7.1.1, this sphere definitely gained electrons. And then 7.1.2 says, calculate the number of electrons gained or lost by sphere A to acquire a charge of minus 5 microcoulombs. The number of electrons gained or lost, right, is equals to the change in the charge of the sphere divided by the charge of an electron, right? So this change is going to be the charge of the sphere final, which is minus 5 times 10 to the minus 6, right? And then initially our charge was neutral, so we have minus 0 here. And then we can divide all of these by the charge of an electron, right? We know fully well that the charge of an electron is minus 1.6 times 10 to the minus 19. So the answer we get in here will be 3.125 times 10 to the 13 electrons. I feel like I've solved this problem before somewhere. Just can't remember. But then anyway, stories in passing. And then 7.1.3 says, let's calculate the electric field at point P due to charge the sphere A. And then the mark allocation is 5, right? We're waiting for 5 marks, which doesn't make any sense because this question is very simple and straightforward. We don't deserve 5 marks. But then anyway, the examiners make the rules. So we have the electric field being equals to K multiplied by the charge of the sphere divided by the distance squared, right? We know fully well that K is a constant. That is 9 multiplied by 10 to the power of 9. And the charge on our sphere, right, is 5 times 10
to the minus 6. We have already established that the distance is 100 millimeters, right? So that 100 millimeters, to convert it to meters, we divide by 1000, right? So we're going to have 100 divided by 1000 squared. And then if you punch that in your calculator, you're going to get 4.5 times 10 to the 6 newtons per coulomb of charge. And just like that, you've earned yourself 5 marks, right? Which is, yeah, unheard of. And then 7.2 says an identical sphere B, here it is here, carrying an unknown charge placed on an insulated stand is brought closer to sphere A. Yes, sphere A. And then charged sphere A shrinks to the right and comes to rest so that the string makes an angle of 30 degrees with the vertical, and the tension in the string is 25 newtons. The distance between the two charged spheres is 50 millimeters as shown in the diagram below, right? And then without wasting any time, 7.2, so 7.2.1 says, is the charge on sphere B positive or negative? Give a reason for your answer. So we have sphere B here, right? And then we have sphere A. And then when sphere B is moved closer to sphere A moves further away, right? So they should have like charges, right? That's why they're repelling each other, so to say. So now we can conclude that sphere B has a negative charge, right? Why are we saying it has a negative charge? Even the question says we should give a reason. It has a negative charge because it is repelling sphere A, and sphere A has a negative charge. So sphere B must have a negative charge consequently, right? Yeah. And then 7.2.2 says, so let's calculate the magnitude of the charge on sphere B. Yeah, here that's, where it starts to get a bit complicated. Let's calculate the magnitude of the charge on sphere B. So problem solving 101. Let's look at the information we have, right? So with regards to sphere B, we know the distance R away from sphere A. We know K is a constant, right? We know the charge of sphere A, and then we don't know the charge of sphere B. That's what we're looking for, right? Another thing we don't know is the electrostatic force between A and B, right? If we can find the electrostatic force between A and B, then we can use F is equals to K Q1 Q2 divided by R squared, right? We have R squared already. We have Q1, we don't have Q2, we have K. So if we find F, then we can find the charge on sphere B, right? So how can we possibly find that F? We can use sphere A, right? Here in this question, you don't have any option. You have two spheres, A and B. We have exhausted all our options with regards to sphere B, and we can't find a way to go to the answer. We are definitely going to use sphere A. So sphere A is at rest there, right? If sphere A is at rest, then FB on A should be equals to the tension force, because the electrostatic force of B on A is moving A to the right, and the tension is holding A from moving to the right, and then A is at rest. So these two forces are balanced, right? And then if we can find the X component of the tension, then we can find FB on A, right? So let's see what happens. So FB on A will be equals to the X component of the tension, right? Because clearly the tension is acting at an angle. Let me make it a bit more clear. So we have sphere A here, right? And then FB on A is pushing to the right? And then the tension is acting at an angle. So if we resolve the tension, then we're gonna know the magnitude of FB on A, right? So now we can say that the tension is 25, right? Multiply by, if you want to find the x component, you use cos on a flat surface, right? And then on an inclined, you use sine. And then the angle that you use is not this 30 degrees that we have here. You use the angle between the force and the x component. Since that angle, this angle here is 30, right? This angle here will be 90, and the angle we're supposed to use is this 60 degrees here, right? So now we can say cos of 60 degrees. So we have 25 multiplied by cos of 60. 25 multiplied by cos of 60 is 12.5 newtons, right? So now we know FB on A. We can use this formula here to find the magnitude of charge P. Right? A very interesting problem. So now we can say FB on A is equals to K, the charge of B, the charge of A divided by the distance between them squared, right? So what is FB on A? FB on A, we know fully well that that's 12.5, right? K is a constant, 9 times 10 to the 9, and then the charge on B is what we're looking for, and then the charge on A, that is 5 times 10 to the minus 6, right? Divided by the square distance between them, 50 millimeters. If it is millimeters, then we have to divide it by 1,000 so that we can convert it to meters. So we have 50 divided by 1,000, and then let's not forget to square, right? And then now you can see that we have solved the conceptual physics problem. We're just doing the math. We're solving for Q of B, right? So here what we're gonna do, we're gonna cross multiply. If we cross multiply, we're gonna get 12.5 multiplied by 50 divided by 1,000 squared, being equals to 9 times 10 to the 9 multiplied by 5 times 10 to the minus 6 multiplied by the charge on B, right? So now it should be easy to see now that if we divide both sides by this term, we should get the charge on B, right? So consequently, the charge on B will be equals to 12.5 multiplied by 50 divided by 1,000, without forgetting to square, right? Everything divided by 9 times 10 to the 9 multiplied by 5 times 10 to the minus 6, and then the charge on B will be equals to 6.9444 times 10 to the minus 7 Coulomb.
Coulomb's law in words, right? We know that F is equals to K Q1 Q2 divided by R squared. So from this equation here, we can see that the electrostatic force that one point charge will exert on another will be directly proportional to the product of their charges and inversely proportional to the square distance between them. So when you're in the exam and you don't remember the formula fully well, you just write down the equation and it becomes fully clear, right? The electrostatic force that one point charge will exert on another will be directly proportional to the product of their charges and inversely proportional to the square distance between them. Obviously, when you substitute the charges, you don't put the size, right? You just put the magnitude. And now we can do 9.2. 9.2 is saying, let's draw a vector diagram of the forces acting on sphere A indicate at least one angle. So let's look at sphere A, right? So sphere A is hanging from a string of negligible mass, right? And then it's interacting with sphere B. So our sphere A here is positive, right? Here's the charge. And then sphere B is negative. Here's the charge, right? Minus 8 times 10 to the minus 9 coulombs. So how does a positive charge interact with a negative charge? They attract each other, right? So sphere B will be pulling sphere A to the left, and then sphere A will be pulling sphere B
to the right. So if we draw in a vector diagram of the forces acting on sphere A, then we should have a vector that shows the electrostatic force that sphere B exerts on sphere A, right? And then apart from that, there's a gravitational force acting on sphere A, right? So we should have another vector pointing downwards, which we can name weight or FG, right? And then last but not least, we have the tension force from the string acting at an angle, right? So the tension force is stopping sphere A from falling down because of gravity, and then it's stopping sphere A from moving to the left, right? So this tension should look like this, right? And then there we have our tension force, and then they say we should include at least one angle. So you can just include the angle that is already there, which is 20 degrees, or you can put an angle here which is 70 degrees, right? And then now we have a vector diagram for sphere A, and we can go ahead and do 9.3. So 9.3 says that let's calculate the magnitude of the electrostatic force that sphere B exerts on sphere A, right? So again, we're saying that the electrostatic force is equals to K Q1 Q2 divided by R squared, right? So we have the charges of Q1. Let's say Q1 is sphere A, right? So we know the charge of sphere A, we know the charge of the second sphere, charge B, right? And then we know K, that's a constant, right? And then now let's look for R squared. The distance between them is given as 3 centimeters. So we're gonna say that R is equals to 3 centimeters divided by 100. We're converting it to meters, right? From centimeters to meters, you divide by 100. So now we can say that the electrostatic force will be equals to, so what is K? We know fully well that K is 9 times 10 to the power 9. And then the charge on Q1, right? We are only interested on the magnitude. We don't put the sign, right? So we're going to have 7 times 10 to the minus 9. And then Q2, which is sphere B, we're going to have 8 times 10 to the minus 9. We only put the magnitude and not the charge, divided by R squared, right? R, we see that is 3 centimeters. You convert it to meters by dividing by 100, and then you square. If you punch that in your calculator, you should get 5.6 times 10 to the what? To the minus 4 newtons, and that's the magnitude of the electrostatic force that sphere B exerts on A. It's also the magnitude of the electrostatic force that A exerts on B, right? Now let's do 9.4. 9.4 says let's calculate the magnitude of the tension force in the string, right? So there's two ways of approaching this question, the magnitude of the tension force on the string, right? So again, our vector diagram for A, right? We had Fe, the electrostatic, and then we had Fg, and then we had the tension at an angle, right? We have already deduced that this angle here is 70 degrees. Why are we saying it's 70 degrees? The angle here is 20, the angle here is 90, so that angle here should be 70 degrees. So because the sphere A is not going up or down, right? The y component of the tension force should be balancing with Fg, right? But then still at the same time, the sphere A is not going to the left or to the right. So the x component of the tension force, right, should be balancing with the electrostatic force. So if you equate these two, you should be able to get the tension force. And then if you also equate these two, you should be able to get the tension force because they are balanced, right? But then let's do both. So let's equate the y component of the tension and Fg, right? So we have Ty being equals to Fg. So what is the tension force? We don't know what the tension force is, but then how do we find the y component? We multiply by sine of theta. We know that theta is 70 degrees, right? So we're going to have multiply by sine of 70 degrees being equals to Fg. Fg is the mass multiplied by the gravity, right? If you look at our equation here, we're told that the sphere has a mass of 0.2 grams, right? So we're going to have 0.2 divided by 1,000. Why are we dividing by 1,000? The SI unit of mass in physics is kgs, right? So we have to divide grams to 1,000 to convert to kg. Multiply by 9.8. So now we can say that the tension is equals to 0.2 divided by 1,000 multiplied by 9.8, and then everything divided by sine of 70 degrees. We just simply dividing both sides by 70 degrees, right? And the tension should be equals to 2.0857 times 10 to the minus 3 newtons, right? So we've used the first way to calculate it. Let's use the other. So the other way, we're saying that the x component of the tension will be equals to the electrostatic force, right? So now we're going to have the tension multiplied by, if you want to find the x component, you take cos of the angle. So we have cos 70 being equals to the electrostatic force. We calculated the electrostatic force in 9.3, right? We know fully well that it is 7.13 times 10 to the minus 4, right? So now we divided both sides by cos of 70. So the tension is going to be 7.13 times 10 to the minus 4 divided by cos of 70, and that is equals to 2.0847 times 10 to the minus 3 newtons. As you can see here, we have 2 points P and T that are situated 3 millimeters apart in the electric field of positive charge Q as shown below. Yeah, it's easy to see. And then for 10.1, the question says that let's draw the electric field pattern around charge Q. Clearly, charge Q is positive, so the electric field lines should be radiating outwards, right? So in your answer book, we should see something of this manner. And then if it was the other way around and the charge Q was negative, then the electric field lines should be pointing towards the charge itself and not outside. Your electric field lines should be evenly separated and they should be of equal length, right? And then let's do 10.2. So we are told now that the magnitude of electric field at point P is 4 times 10 to the power 6 newtons per coulomb. So for the sake of clarity, let's just, write that down before we solve any problems. So we're saying that the electric field at P, right? So we're calling that EP, is equals to 4 times 10 to the 6 newtons per coulombs, right? And then at point T, the magnitude is 2.5 times 10 to the 5 newtons per coulomb. So again, for the sake of clarity, let's say ET, right, is equals to 2.5 times 10 to the power 5 newtons per coulomb. And then 10.2.1 says, let's calculate the ratio of the electric field at point P to the electric field at point T. Write the answer as EP is to ET. So let me make an example here. Let's say we had X is equals to 6 and Y is equals to, let's say Y is equals to 3, right? And we're saying that let's find the ratio X is to y. The ratio x is to y, you will do the following. So you would say x is to y. In place of x, you put in 6, and then in place of y, you put in 3. Right? But then you can see that you can divide both sides by 3, and then if you do that, you're gonna get 2 is to 1, and that's the ratio of x to y. So we are applying the same idea here, right? We're saying that EP is to ET, but then what is EP? We know fully well that EP is 4 times 10 to the 6 newtons per coulomb. And then what is ET? That is 2.5 times 10 to the 5 newtons per coulomb. Right? So we are dividing which number by which number here, because it's no longer straightforward, like for instance when you have 6 and 3, right? So we divide both number by the smallest. Clearly, between 4 times 10 to the 6 and 2.5 times 10 to the 5, 2.5 times 10 to the 5 is the smallest one. So we're going to divide by 2.5 times 10 to the 5 on both sides. So on the right hand side, we essentially dividing it by itself, so we should get 1, right? And then now we're gonna say 4 times 10 to the 6 divided by 2.5 times 10 to the 5, right? That should give you 16. So EP is to ET as a ratio of 16 is to 1. And now let's do 10.2.2. 10.2.2 is a bit complicated. There's some math here that is involved, right? But let's see what we can do. So he's saying, let's find the distance between charge Q and point P. Charge Q and point P, right? So let's see what we can do here. So obviously we can say EP is equals to KQ divided by R squared, right? That's the formula we have for the strength of an electric field at a given point, right? But then, lucky for us, we know fully well what EP is. EP is 4 times 10 to the power of 6, which is equals to K. K is a constant, that is 9 times 10 to the power 9. And then Q, at this point, we don't know the value of Q, right? So we'll just put it as it is. And then from Q to P, we don't know the distance. That's what we're looking for. So let's just put R squared, right? And then, yeah, you should be able to see now that we're stuck. We have 2 variables and 1 equation. So we need another equation. How can we find another equation? We can use point T. So let me show you what I'm talking about, right? So here, just to finish this off, let's cross multiply. If we cross multiply, we're gonna get 4 times 10 to the 6 multiplied by R squared is equals to 9 times 10 to the 9 multiplied by Q. And then we can call this our equation 1, right? And now to use point T, we're going to say that ET is equals to KQ divided by R squared. And then what is ET? We know fully well what ET is again, right? That is 2.5 times 10 to the 5 being equals to 9 times 10 to the 9. And then what is Q? We still don't know what Q is. And then now what is R squared? Now R squared is the distance from Q to T, right? We already established that the distance from Q to P is R, right? So QT should be R plus this 3 millimeters here, right? It's only fair. So we're gonna have R plus 3 millimeters, right? We don't deal with millimeters in physics, we deal with meters, so we have to divide that by 1,000. So we're gonna have 3 divided by 1,000 squared, right? Now you can see that you have 2 variables. We're gonna end up with 2 equations, and then we're gonna find R, right? Therefore, so if we cross multiply here, we should get 2.5 times 10 to the 5 multiplied by R plus 3 divided by 1,000 squared being equals to 9 times 10 to the power of 9 multiplied by Q. And then what are we calling this one? We're calling this one equation 2. So you can see that 9 times 10 to the 9 multiplied by q is equals to this expression here. But then at the same time, 9 times 10 to the power of 9 multiplied by q is equals to this expression here. So we can equate the two expressions. We're only going to have r as our variable, and we're going to try and solve that. So if we do that, we can say that equation 1 is equals to equation 2, obviously, because they're all equals to 9 times 10 to the 9 multiplied by q. So equation 1 there was 4 times 10 to the 6 multiplied by r squared. Yes. And then our equation 2, we have 2.5 times 10 to the 5 multiplied by r plus 3 divided by 1000 squared, right? So a lot of people, when they get to this step, they're going to solve this square here, right? But then if you do that, the problem becomes very complicated. So what I want you to do instead, you take square roots on both sides so that you don't have to square anything and end up having to solve a quadratic equation, right? So let me show you what I'm talking about. So we're going to take the square root on the left hand side, and we're also going to take the square root on the right hand side. If we do that, we're gonna get the square root of 4 times 10 to the power of 6 multiplied by, instead of r squared, now we just have r, right? And then on the right hand side, we're going to have the square root of 2.5 times 10 to the power of 5. And then instead, this square here that I'm circling right now is going to fall off, right? Because we're taking the square root. So we're just going to have r plus 3 divided by 1000. And then we don't have the square root anymore, right? So now we're gonna multiply out the right hand side. After we multiply out the right hand side, we're just going to solve for r. So let me show you what I'm talking about. So we're gonna have the square root of 4 times 10 to the 6 multiplied by r being equals to the square root of 2.5 times 10 to the 5 multiplied by r plus the square root of 2.5 times 10 to the 5 multiplied by 3 divided by 1000. So now we have r here, and then we have r here. We group in the like terms. So we're going to have 4 times 10 to the 6r minus the square root of 2.5 times 10 to the 5 r being equals to 2.5 times 10 to the 5 multiplied by 3 divided by 1000. So I'm actually not going to put this in the calculator, right? I'm just going to take r as a common factor. So if I do that, I'm going to get 4 times 10 to the 6 minus 2.5 times 10 to the 5. R is a common factor, and this should be equals to the square root of 2.5 times 10 to the 5 multiplied by 3 divided by 1000. I hope you're having as much fun watching this video as I'm having making it. So now I'm going to divide both sides by the coefficient of r, right? And then if I do that, I should get r is equals to the square root of 2.5 times 10 to the 5 multiplied by 3 divided by 1000, right? And then now we're dividing by that coefficient, which is the square root of 4 times 10 to the 6 minus the square root of 2.5 times 10 to the 5. And then now you can finally put this expression in the calculator in attempt to find the final answer, right? And you should get 0.001 meters, right? That is also equals to 1 millimeter. So the distance between Q and point P is 1 millimeter, or 0.001 0.001 meters. And finally, to find the magnitude of charge Q, the magnitude of charge Q, right? We can use the electric field at P or at T, right? It doesn't matter right now because we have R. It will be easy to find Q, right? So let's just use EP. So we have EP is equals to, so we have KQ divided by R squared, right? But then EP is given to us. We know fully well that that is 4 times 10 to the 6 being equals to 9 times 10 to the 9 multiplied by Q, and then we divide in everything by 0.001 meters, right? 0.001 meters, and then we shouldn't forget to square. So now yeah, we can cross multiply. If you cross multiply, you get 4 times 10 to the 6 multiplied by 0.001 squared being equals to 9 times 10 to the 9 multiplied by Q. You divide both sides by 9 times 10 to the 9, right? So you should get Q is equals to 4.44 times 10 to the minus 10 coulombs.